any time. We don't lose any time by switching laptops. And with that, I will hand over to Arshavir, sorry, for the first talk, and it's actually from ETH Zurich. Thank you.
Thank you very much for the introduction. Can you hear me? Okay, so my name is Arshavir Ter-Gabrielyan, and this is joint work with Alexander Summers and Peter Müller. What we did in this work is developed a modular technique for reasoning about heap reachability. So first of all, let's talk about why is heap reachability interesting. Well, it's an essential specification ingredient for heap manipulating programs. Take a garbage collection, for instance. A typical garbage collector starts traversing the heap from some root node and indicates and marks the nodes that are still in use to indicate those that can actually be freed afterwards. So in order to specify that a garbage collector behaves correctly, we need to be able to say that that all nodes that were reachable from the root node are actually marked, but also that nodes that haven't been reachable from the root node remain unmarked. Another example is acyclicity. Many algorithms require acyclic data structures to operate correctly. And in order for us to be able to specify acyclicity, we need to be able to say for each pair of nodes x and y that they are not mutually reachable from one another. So we're interested in reasoning about reachability in a way that is modular, and this is why we choose to build our technique on top of separation logic, which offers a state-of-the-art methodology for modular reasoning about heap manipulating programs. And the most interesting aspect of modular reasoning is typically about how can we support procedure calls. So let's look at this example. Here we have a call to a procedure called concat that concatenates two singly linked lists starting in x and y. The first thing that we do is we assume something about the heap configuration in the pre-state of the call. In separation logic, every procedure must somehow explicitly specify the set of memory locations that it operates on. And we depict this set using this pink box. Now we have to split this set into the part of the heap that is narrower that the called procedure is operating on. And this is what we call the footprint of the call. And there's also the leftover part of the heap that is called the frame. Now what's special about the frame is that the heap configuration in the frame is guaranteed not to be affected after the call. So it remains unchanged. Conversely, the heap configuration in the footprint will change according to the specification of the procedure. And now what's left to do is to join the two subheaps, footprint and frame, in order to obtain the information about the heap from the client's perspective in the post-state of the call. Together, this mechanism is called separation logic framing. And what it's very useful for are essentially those program properties that can be disjoint, that can be specified for disjoint fractions of the heap. Okay? For example, if we assume that we have a number of linked lists before the call, then we invoke the call. We can use separation logic framing to show that we still have a number of singly linked lists in the program state after the call. But how do we talk about heap reachability in this setting? For this purpose, we defined a novel notion of local reachability. And this allows us to specify the existence and the absence of paths within certain fractions of the heap. For example, if we denote a heap fraction through G, then the ternary relation local path over gxy denotes that there exists a heap path from x to y that goes only through the nodes in G. In particular, this implies that x belongs to G, but y doesn't have to belong to G and can still be reachable from its nodes. So here's a concrete example. In this example, there does not exist a G local path from U to V, because in order to reach V starting from U, we would need to traverse the heap exiting G and then come back into it. but there does exist a G-local path that connects V to U. Since we're interested in reasoning about an unbounded paths of unbounded length, we abstract over the concrete heap edges by using these wavy arrows that depict the local reachability information that is known so far. Okay, so now we have the means to talk about reachability in a modular way. Let's return to the discussion about procedure calls. And here we have some procedure proc that is invoked. And again, we need to assume something about the heap configuration in the pre-state of the call. And here, for example, we assume that it is known that, that X reaches Y through a client local path. Okay? So in order for us to split the heap into two, we need to represent client local reachability information using footprint local and frame local reachability information. And what does this mean in practice? Well, for each path, for each client local path, we would need to be able to represent it using only some number of footprint local and frame local subpaths. And if we can do this, then we can apply separation logic framing just like before, because the state of the heap in the frame will not be affected by the call, and the state and the configuration of the heap in the footprint will change according to the specification of proc. For instance, it can be specified in its post condition. Finally, we can join the two heaps, and this way we can obtain the client local reachability information in the post state of the call. So this demo works out nicely, and the reason for that is mostly that we assume complete knowledge about all heap edges. But in practice, what we're interested in is performing similar reasoning steps without having full information about the heap edges. So assume that we only have local reachability information. And how do we perform these reasoning steps? It turns out that this is a fundamental problem. So next we will show how exactly, so why is it exactly does this problem take place? And for that purpose, let's consider a special case in which we assume that there exists a client local path from X to Y that starts and ends in the footprint. One possibility is that this entire path fits inside the footprint, and then there's the corresponding local path predicate that we can infer. But it could also be that the shape of this path is more complex, and that it spans beyond the boundary of the footprint, exiting it and entering it back again to reach its destination in Y. But then we would be able to infer the information using a combination of local reachability predicates that describe each of the subpaths into which the original path from X to Y has been fractured. Unfortunately, this is not it. The situation could be worse if the original path from X to Y crosses the boundary of the footprint multiple times. Then we will have yet another possible configuration, yet another possible combination of our local predicates that describe this situation, right? So this can go on, and on top of that, we can also we also need to consider all combinations of the listed cases, because there could exist alternative paths that connect X to Y. So far, it's clear that the number of cases that we would need to analyze is unbounded. And this is the fundamental problem. And in particular, this impedes our chances of achieving automatic reasoning. So what do we do about this problem? Well, what we would like is to identify a viable simplification of the original problem that actually has a solution. And on the one hand, we would like it to power a technique that is expressive enough to support common data structures. And on the other hand, we would like our technique, so we care about automation, so we would like our technique to be reducible to first order reasoning that automatic SMT solvers can handle efficiently. Okay, we have identified the simplification that satisfies these criteria. We call it relatively convex footprints. Intuitively, a footprint is relatively convex if, while walking along paths that exit this footprint, one cannot come back into it. Why is this a useful simplification? Well, because it allows us to avoid the problematic configuration that we experienced before, where heap paths could span the boundary of the footprint, crossing the boundary multiple times in many different places. Relative convexity is a restriction that we impose on all procedure footprints in our technique. And this is the essential bit that empowers the most fundamental aspect of our technique. So next, let's discuss how exactly does it help to solve the original problem that we've seen before. For that purpose, let's zoom in into this relatively convex footprint and return to the special case that caused trouble before. So here again, we assume that there exists a client local path from X to Y that starts and ends inside the footprint. And the point that we want to make is very simple. We would like to argue that this path cannot look like this. So it cannot first reach some nodes of the frame and then return back into the footprint, reaching a destination in Y. Because indeed, this would violate our assumption of relative convexity of the footprint. In other words, the client local path from X to Y exists if and only if there exists a footprint local path that connects these nodes. And this can be explained using a very simple first-order formula that covers this special case. Now, this formula enables both splitting and joining heap paths, which we together call path partitioning. If we read it from left to right, then we split the path. If we read it from right to left, then we can join the paths back. Notice that if before we needed to consider an unbounded set of possibilities, here we only have one possibility to consider. So for the remaining cases, which mean for all client local paths that don't fall into this first special case, we identify a way of reducing the reasoning steps using the same argument as before. For instance, if a client local path starts in the frame and ends in the footprint, then it must cross the boundary of the footprint at least once in order to enter it. So let's denote through A the first node along this path that belongs to the footprint. Now, for the client local path from A to Y, we can reuse the same argument as we had in the first case. Ultimately, this gives us a way of splitting this path into exactly two subpaths. And again, instead of an unbounded number of cases, we get exactly one case. An analogous situation is for client local paths that start in the footprint and end in the frame. The final possibility is if our client local path starts and ends in the frame, and this is a bit more subtle. So in the paper, we identified that it's actually important in certain subtle cases to be able to distinguish whether the path of this kind goes entirely through the frame or whether it enters and exits the footprint once. But the idea of relative convexity is again crucial here, and it allows us to reduce an unbounded number of cases in the analysis to a finite case analysis. So overall, our technique is mathematically sound and complete, as we explain in the paper. So let's summarize the findings so far. Given a relatively convex footprint, for each client local path, we have a deterministic way of splitting this client local path, of representing this client local path, using a finite number of only footprint local or frame local subpaths. And this is exactly what we wanted to achieve. Let's talk about expressiveness. Firstly, we support arbitrary directed acyclic graphs and a rich spectrum of relatively convex decompositions for these. We also support a class called 0-1 path graphs, which is defined as structures in which between every pair of nodes there exists a unique path modular cycles, and we support relatively convex decompositions for this class as well. How does the expressiveness compare to state of the art? So Grasshopper is a tool for automating separation logic reasoning with reachability predicates, but the structures that it supports are limited to various tree and linked list structures. Sakai Zaki et al. Published a work in Popl 14 that gives a way of modular reasoning about heap reachability, but their setting is restricted to the decidable fragment of first-order logic, and effectively, this reduces the supported structures to various kinds of linked lists. So, to our knowledge, all other categories that we list here are enabled by our technique for the first time. We have evaluated our technique based on a number of benchmark examples that we found in literature, and all of our experiments are publicly available online. So the first thing that we did, we created a lightweight encoding of the technique into the Viper verification infrastructure. Viper is a powerful tool for automating separation logic reasoning. And then each of the cases we verified using Viper's verification condition generator that works on top of the Z3 SMT solver. So a little overview of the evaluation. We cover both supported classes, DAGs, as well as 0-1 path graphs. And we additionally consider a number of buggy examples in which the bug has been nested either in the implementation or the specification of the code. And to give you an idea on the variety of the examples, so here we indicate those that support multiple outgoing heap edges per node. And here we indicate those that support sharing, which means multiple incoming heap edges per node. And finally, we indicate the cases in which procedure calls are featured, and therefore we need our technique for convex framing. So it's particularly interesting to take a look at two cases. In the first two variants of our merge example, the only difference is that in the DAG variant, we lift the restriction that nodes must be unshared. And this gives us a strict simplification of the overall verification condition. And as you can see, the overall verification time goes a bit down. Another observation is here. So our sorted variant of ring insert took significantly longer to verify, and this is due to the fact that here we combine reachability specifications and value properties and verify them at the same time. Now, quickly summarize parts of the work that are not in focus of this talk, but you can find them in the paper. Firstly, we need to be able to recover reachability information after changes to individual heap edges. And we explain how to do this in the paper. And finally, reasoning about heap cycles requires additional machinery that we also present in the paper. So to sum up, the key idea in our work is relative convexity. We require all procedure footprints to be relatively convex, and this allows us to reduce a previously unsolvable problem to the one that we can actually solve in an elegant way. And our technique is expressive, supporting common data structures. And finally, we show that there exists an encoding of our technique that demonstrates that it can be efficiently automated using common SMT solvers. Thank you very much for your attention, and I'm happy to take your questions.
Due to the lunch queuing problem, we have time for one question, unless you insist that there need be more. Any questions? Yes, please. This is too far. You have to wait for the microphone.
Hi, two questions. One is, in your experiments, did you do union find? You mentioned it earlier, but then I didn't see it in your experiments. And secondly, did you allow for a node to be deallocated, or was that not possible in your language framework?
Could you repeat the second one, please?
Did you allow a node to be deallocated? Because one of the issues is a node from the frame that's pointing into the local heap, which is then deallocated, and therefore you have a junk pointer pointing into the local heap. Mm-hmm. And I'm curious whether you handled that or whether that's not possible in your setting.
So with respect to union find, we have an experimental encoding for the find procedure, but for some reason we didn't have time to encode union. But I think that our methodology applies there, so we could extend our evaluation on this example. It would make sense. As for Memory deallocation, we haven't focused on this aspect, but in our technique, I expect this to be easily supportable. We can talk about that offline, I guess.
Okay, thank you. Speaker again.